Okay, now power of a lens. What is the power? We know that the convex lens focus the light or the beam of a light incident on it. That means if the parallel rays are incident on a convex lens, they are focused at the principal focus of a lens. While in case of a concave lens, if the beam of the parallel light is incident on it, so this parallel beam after the reflection not focus but there is the diverse. Therefore, the convergence and divergence capacity of a lens is known as the power. Power is the capacity of a lens to converge or diverge the incident light on it, that is known as the power. So how much the lens can focus or diverse, whatever the light incident on it, this capacity is known as a power. A lens with the shorter focal length bend the incident light more. That means the bending of a light incident on a lens, that is also depends on the focal length of a lens. Focal length of a lens. So that is also important for the objective question. A lens with the shorter focal length bends the incident light more. Now, another definition of the power for the equation, the power of a lens is defined as the tangent of an angle by which it converges or diverges a beam of light falling at unit distance from the optical center. In case of a convex lens, what is the optical center? If the light incident on a convex lens at unit distance from the optical center, this incident light is converged or the diverse at whatever the angle, the tangent of this angle is known as the power. Again, the definition of power is that the tangent of an angle by which it converges or diverges a beam of light falling at unit distance from the optical center. Here the beam of light is incident at unit distance from the optical center. After the incidence, the tangent of angle at which it converges or the diverges. Therefore, the power P is equal to tan delta. From figure, the tan delta is equal to H upon F. From figure, we consider this angle triangle. So this distance is H and this distance is focal length of a convex lens. Therefore, tan delta is equal to H upon F. But here in our definition, the beam of light incident at unit distance from the optical center, therefore H is equal to unit distance. Therefore, tan delta is equal to 1 upon F. Now, here the angle is very small, therefore tan delta we consider as a delta is equal to 1 upon F. Therefore, the power of a lens P is equal to 1 upon F. We know that the focal length is measured in centimeter over the meter. Therefore, the SI unit of a power is meter inverse, and that is known as the diopter. That is known as diopter, and that is denoted by capital D. Capital D. Therefore, 1D is equal to 1 meter inverse. Therefore, the power of a lens of focal length 1 meter is 1 diopter. Definition of 1 diopter. The power of a lens of focal length 1 meter is known as 1 diopter. Now, for convex lens, power is positive, and for concave lens, power is negative. So keep in mind this SI unit frequently asked in board exam for 1 mark subject question, and definition of the diopter. The power of lens of focal length 1 meter is blank is given. Actually, that is the 1 diopter. Power of a convex lens is positive, power of a concave lens is negative. Okay. Now we are familiar with this type of the SI unit when we check up our eye for the, if we are not seeing the object clearly. At the time, the optician prescribes the number. If an optician prescribes a corrective lens of the power, suppose the plus 2.5. whatever the prescription is given by the optician for our correct vision of our eye. So that is given in that form, plus 2.5D or the minus 2D. This type of the correct number is given. So what is the meaning of this plus 2.5D? Plus, that means for this correction we require the lens is convex lens because there is the positive. And focal length f is equal to 1 upon p. 1 upon p is equal to 1 upon 2.5. That means the 40 centimeter focal length of this convex lens is required for our eye of a correction. Suppose sometimes the number is like this: a lens of power of minus 4D. Here the negative sign indicates that here the concave lens is required for the correct vision of our eye. Means a concave here of focal length 1.4, that means the 25 centimeter. There is okay. So there is the meaning of the power, and what is the SI unit and what is the equation? Equation of power P is equal to 1 upon F, or the tan delta is equal to 1 upon F, that is known as the power. So there is the SI unit and power. Now, after discussion of the power P is equal to 1 upon F, there is the relation between the power and focal length. What is the equivalent focal length of the if more than 2 or the 2 or more than 2 lenses are used in combination? So, what is the equivalent equation of focal length for the combination of more than 2 lenses? At that time, to obtain the equation of equivalent focal length of combination of 2 thin lenses placed in contact with each other. What is the equivalent power, what is the focal length, and what is the magnification? And frequently we are using this combination of the lenses in telescope, microscope, right? To get the maximum magnification and to obtain the image of the object is clear. So here the combination of the lens are required. Okay. Now listen, so first the description of figure. Our aim is to obtain the equation of equivalent focal length of combination of 2 thin lenses placed in contact with each other. Therefore, first the description as shown in figure. As shown in figure, 2 thin lenses, 2 thin convex lens A and B of focal length f1 and f2 are placed in contact with each other, and their axes are coincide. Axes are coincide. Now, the point of contact of these 2 lenses is known as the contact point, or there is the optical center. With respect to this point P, all the distances are measured in combination. The point of contact is known as center point. Center point P. Center point. Okay. The point object O is placed at distance u from the P. The image formed by the lens A is I. This image acts as a virtual object for lens B, and final image I is obtained. Now, a point like object, a point object O is placed at distance u from P. The image of object O is the image of object O is I1 formed by lens P. Now this image acts as a virtual object for lens P. Such image act as a virtual object for lens P. Lens and final image I is formed. Therefore, for lens A, equation of lens is minus 1 upon u plus 1 upon v1 is equal to 1 upon x. And for lens B minus 1 upon v1 plus 1 upon v is equal to 1 upon f2. There is equation 2, that is 1. But the final image is formed to the combination of these two. Therefore, we have to add these two equations. Now, adding equation 1 and 2. Adding equation 1 and 2. What's happened here? First, the addition of the left hand side minus 1 upon u plus 1 upon v1. Left hand side of equation 1, left side of equation 2, minus 1 upon v1 plus 1 upon u, 1 upon v is equal to 1 upon f1 plus 1 upon f2. Now, second and third term, 1 upon v1 minus 1 upon v1 cancel, therefore minus 1 upon u plus 1 upon v is equal to 1 upon f1 plus 1 upon f2. So that shows that the object distance is u and final distance is v. That means, yes, we use the single lens instead of these two lenses. At that time, the object distance is u, image distance is v. Suppose the equivalent focal length of this lens is f. If an equivalent focal length is f, then minus 1 upon u plus 1 upon v is equal to 1 upon f is equal to 1 upon f1 plus 1 upon f2. 1 upon f1 plus 1 upon f2. Now, if n lenses of focal length f1, f2 and so on, fn are placed in contact, its equivalent focal length is 1 upon f is equal to 1 upon f1 plus 1 upon f2 and so on, 1 upon f. So there is the equation of equivalent focal length for the two thin lenses are placed in contact, and if more than two, that means the end number of the lenses are placed in contact, at that time the equivalent focal length of this combination is given by this equation. So there is the focal length for combination of two thin lenses. Now we can also That was the equation of equivalent power and also equivalent magnification. So here the answer of this question is complete, but we also had done the equation of power and magnification. Okay, now what is the equivalent power of two thin convex lenses placed in contact with each other? We know that the power is equal to 1 upon F. Therefore, the power of lens A, is, there is the P1 is equal to 1 upon F1, and power of lens 2, so the lens B is, there is the P2 is equal to 1 upon F1. Right? And equivalent focal length of combination of two thin lenses is 1 upon F is equal to 1 upon F1 plus 1 upon F2. Now we will substitute the value of 1 upon F1 as power P1. 1 upon F2 is as power P2. Therefore 1 upon F is the equivalent power of this combination. Therefore P is equal to P1 plus P, where P is equal to 1 upon F is equal to equivalent power. Thus, the equivalent power is equal to the sum of, or the algebraic sum of power of each lenses are in contact. Right? Thus, equivalent power of combination is equal to the algebraic sum of power of each lens. Suppose here one is convex, second is the concave. For the concave, the power is negative, convex, the power is positive. Right? Therefore, according to the lens, we can substitute the value of power. For the convex, positive value. For concave, the power is negative. Okay. Now, after that, what is the equivalent magnification? For that purpose, equivalent magnification. Okay. Now, what is the magnification for lens A? For lens A, object distance is u, image is permanent V1. For lens A, object distance is equal to u. Image distance is equal to V1. Therefore, magnitude of magnification mode of M1 is equal to V1 upon equation 1. And for lens B, what is the object distance? What is the image made by the lens A act as virtual object for second lens? Therefore, for lens B, object distance is equal to V1 and image distance is equal to V. Therefore, magnitude of magnification for lens B M2 is equal to V upon V. That is equation number. Now, magnification is that we know that mod of M is equal to image distance upon object distance. Now we can multiply and divide it by the V1. Therefore, V1 upon U plus V into V upon V1. So that is our M1 into M2. Thus, the resultant or the equivalent magnification is equal to the product of magnification of each lens in combination. Thus, equivalent magnification is equal to the product of magnification of each lens. Of each lens in combination. Okay. What is the use of this combination? The combination of lenses are used in camera, telescope, microscope, and optical instrument. The use of combination of lenses is in microscope, telescope, then camera and optical instrument, etc. So there is the use of combination of that lens. So frequently on the basis of this equation of equivalent focal length, equivalent power, and equivalent magnification, the objective question will be asked. You have to keep in mind that in combination these type of the lenses are equivalent. For convex lens, the power is positive. For concave, power is negative. And also we know that for the convex lens, focal length is positive. Concave lens, the focal length is negative. So using this concept with the sign convention, we can find out the resultant focal length and resultant power and also the resultant magnification of combination of lenses. Clear this?